said, hey, you, let's do some DiffEQ. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some DiffEQs. In this video, we're going to talk about linear differential equations. This is a very important class of differential equations. Let's see what they look like. A linear differential equation has the following form. It's worth noting that there are two primary components of a linear differential equation. The first component is all of the magenta functions here. Each one of these functions depends only on the independent variable, which in this case is the variable x. The other major component is that the dependent variable, in this case y, the only thing we are doing to that variable is taking its derivative, or second derivative, or third derivative. That is, orders of its derivative. Here we have the zeroth order corresponding to what we've noted as the a sub 0 coefficient function. Here we have the first derivative corresponding to the a sub 1 function that depends only on the independent variable x. Here we have the n minus 1 derivative corresponding to the a sub n minus 1 function, and the nth derivative corresponding to the a sub n function. Over here we again have a function just of x. So as a reminder, the two big components, the functions of the independent variable and plane derivatives. When I say plane derivatives, I mean we're taking the derivative and not doing anything else to it. We're not taking the derivative and then squaring that derivative, or taking the derivative and then putting that as the argument inside of cosine. We're just taking the derivative, and all that happens is it gets multiplied by one of these coefficient functions. Let's go ahead and look at our first example. In this example, we have the first order derivative and a function x times y. Now let's see if we can match this up with the form of a linear differential equation. Here is the linear form of the differential equation that I've put at the bottom of the screen. And what we have up here doesn't immediately match it, but let's do a little bit of rewriting to see if we can get it to match up. First, we'll take and change from Leibniz notation to prime notation. Then we'll subtract xy from each side. Finally, we'll put the negative x in parentheses, and now I claim this is in a form such that it will match up with this linear form down here. Let's color the y's in yellow, and then let's color function negative x and 0, let's color them in this magenta. Now we'll take this and we'll move it below the linear equation form here, and if I stretch this out a bit, now we can see that it aligns perfectly. I've suppressed notation for the function y being of x. Here this was put for more completeness, but of course down here we're suppressing that notation and just writing y prime and y, but they are functions of x. Since we can write this differential equation in a form that aligns with this general linear equation form, we say that this differential equation is linear. So, awesome. Let's look at another example. Suppose we have this differential equation. Now, once you've become familiar with the linear form, you'll see right away that this is not a linear differential equation. The reason is that we have cosine of y. If you do anything to y besides take its derivative, that automatically disqualifies it from being a linear equation. Let's look at the linear equation again to remind ourselves what it looks like. Looking at the linear equation in its most general form, we notice that as far as y goes, we only take the derivatives of y. We never do something like take cosine of y, or take sine of y, or tangent of its derivative, and so on. All we do is we take derivatives of y and then multiply them by functions of x. This is not just a derivative of y. Therefore, this differential equation is not linear. Let's look at our next example. Here we have a differential equation that's of second order. Let's see if we can get it to match up with the linear equation form. Here's our general linear equation form again. And now, if we try to highlight the components that involve y and then involve x. First, let's do y. Okay, now that we have those colors, now let's look at the coefficients in front of y, and let's color those. If they are just functions of x, we see that it's 3, it's 2, and it's 7. Those are constant functions in terms of x. We can color them, and then this function over here is certainly just a function of x. Then, if we space it out a bit, we see that it will align perfectly to this general linear form. Therefore, this equation is linear. Now let's look at our last example. In this example, we have the following differential equation. Like we've done before, let's try to highlight the derivatives of y and then the coefficients in front of those derivatives. We can match everything up, it'll be linear, and if not, it won't be linear. As a reminder, here's what our linear form looks like. We'll start by coloring the derivatives of y. We've highlighted these in yellow to match up to the general form here. Now let's color the coefficients as far as they are just functions of x. Then we'll color the lone constant function of x on the right-hand side. But now we notice there's a problem. We now have a coefficient function that is not just a function of x. That means that this differential equation is not linear. Well, I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.